study that how we can find out the solution of the time invariant state equations. So let's start with our topic. Now we know that the state equation for the time invariant system, it is given by the formula x dot t equals to axt plus but. Okay, so we have here so for a time invariant system, the state equation is given by, we have x dot t equals to axt plus but. Okay. Now this state equation, it is classified into two groups. First is homogeneous state equation and second is non-homogeneous state equation. And this classification is based upon whether the input is present or absent. Okay, so we have two types of state equations. So it is classified into two groups. First is homogeneous state equation. Now in homogeneous state equation, this input ut, it is not present. So ut is absent here, or we can say that ut is equals to 0. Whereas in the non-homogeneous state equation, ut is present. So we can say that ut is not equals to 0 in the non-homogeneous state equation. So now we are going to study that how we can find out the solution of the two types of the state equations, the homogeneous state equation and the non-homogeneous state equation, considering the two cases that whether ut is present or it is absent. So first we will study the solution of the homogeneous state equation. Okay, so we have our state equation as x dot t equals to axt plus but, and for homogeneous case ut is equals to 0. Now if ut is equals, then this term become 0 because ut is 0. So x dot t is equals to axt. Now taking Laplace transform of this equation, we will get Laplace transform of x dot t is s into xs, and the Laplace transform of xt is xs. So our Laplace transform will become s xs equals to a xs. Okay. Now taking this xs to this side, because we have both the terms in xs, so we will have s xs minus a xs equals to x of 0. Now keep one thing in mind, here we have taken the Laplace transform and we have not assumed that the initial conditions are 0. So we will have to consider the initial conditions also here. This is x0. When you take Laplace transform assuming initial conditions to be 0, then this x0 part is neglected. But here we are taking the Laplace transform and we have considered the initial conditions also. So we have put an additional term here plus x0. So this xs minus axs will be equals to x0. Then we can take xs as common and we are left with S into I will be the identity matrix because A is a matrix and we have to keep both the sides as a matrix to do this subtraction. So here we will have Si minus A and this is X0. Now let's bring this Si minus A to this right hand side. So we will have XS equals to Si minus A inverse x0. Okay. Now this Si minus A inverse is phi s. Phi s is the state transition matrix. So we can have here xs is equals to phi s x0, where phi s is Si minus A inverse and it is known as the state transition matrix. Also STM. Now, if we take the Laplace transform of this phi s, then it is inverse Laplace transform, then it is phi t equals to inverse Laplace transform of phi s. Okay, or we can say that it is the inverse Laplace transform of Si minus A inverse. So this is our state transition matrix. Also, it is known as the resolvent matrix. So whenever you are asked that let's calculate the state transition matrix, so it is the formula for the state transition matrix phi s is equals to Si minus A inverse. Or if you are asked that phi t, then you have to take the inverse Laplace transform of Si minus A inverse. Now there are some properties of this state transition matrix. Let's study, because if we take the inverse Laplace transform, this state transition matrix phi t, it comes out to be e raised to the power a t. Okay, this is another formula for the state transition matrix. So there are some properties of this state transition matrix. Let us study those properties. The first property of the state transition matrix is that phi 0, it means we have the value of the state transition matrix phi t is e raised to the power at. So we are putting this t equals to 0. So here also we will put 0. So its value will come out to be 1. So state transition matrix at time t equals to 0, it is 1. Second property is we know that phi t is e raised to the power at. Now if we take here e raised to the power minus at and then calculate its inverse, then it will be equivalent to this. Because what is phi minus t? We have e raised to the power minus at. Instead of t, we are writing minus t and then we are calculating its inverse. So it is similar to this. So if phi t will be equals to, if we are taking the inverse of phi t, then it will be equals to phi of minus t inverse. Or we can say that phi of inverse t is equals to phi of minus t. Okay. Third property of transition matrix is phi t1 plus t2. That is, instead of t, we are writing t1 plus t2. So it will be e raised to the power a t1 plus t2, or it will become e raised to the power a t1 plus a t2. Or we can say that e raised to the power at1, e raised to the power at2. Or it will be phi t1 plus t2 will be equals to phi at t1 and phi at t2. Because e raised to the power at1 is what? Phi t1, and e raised to the power at2 is phi t2. So we have this expression. Now fourth property is that phi t to the power n. It means that we have e raised to the power at and its power is n. So it will become e raised to the power n at. Okay, or we can say that it is phi n t. That is, instead of t we are writing nt. So it will become e raised to the power n at, and it is similar to phi t raised to the power n. So this is the fourth property of the state transition matrix. Now next we have fifth property, phi t2 minus t1 and phi t1 minus t naught. It is equal to phi t2 minus t naught, or it is equal to phi this. How we can prove this? We have phi t2 minus t1, it means e raised to the power a t2 minus t1. Then phi t1 minus t naught means e raised to the power a t1 minus t naught. So if we expand this, we will have e raised to the power a t2, e raised to the power minus a t1, e raised to the power a t1, and e raised to the power a t naught. So this e raised to the power minus 81 and e raised to the power 81, they will be cancelled out, and we are getting e raised to the power 82 and e raised to the power minus 80 naught. So this will become t2 minus t naught, or we can say that it is phi t2 minus t naught. So we have proved this, that phi t2 minus t1 or phi t1 minus t2 when t naught, when we multiplied, it is equal to phi t2 minus t naught. Similarly, it is also equals to phi t1 minus t naught and phi t2 minus t1. Okay. So these are the 5 properties of the state transition matrix. So we have studied the solution of the time invariant homogeneous equation. Now next we will study the second type of equation, state equations, non-homogeneous type. Now in a non-homogeneous state equation, ut is not equals to 0. This is the homogeneous, non-homogeneous case. ut is not equals to 0. So we have our state equation as x dot t equals to ax plus bu. U is present here. Now taking the Laplace transform of this equation, Laplace transform of x dot t is s xs equals to, we have ax, so it is axs plus x of 0 plus bus. Now taking this excess, bring this to the left hand side, so we will have s excess minus a excess Taking this x as common, we will have Si minus A equals to, now taking the inverse Laplace transform, because we have to find out the solution, so we will take it in solution in the time domain. So we will taking inverse Laplace transform, we will get inverse Laplace transform of xs is xt. Then we have if we bring this Si minus A to the right hand side, it will become Si minus A inverse, and its inverse Laplace transform will be inverse Laplace transform of Si minus A inverse. Then we have x of 0 plus this Si minus A inverse will be also multiplied with this B. So we have here inverse Laplace transform of Si minus A inverse and B and US. It is the inverse Laplace transform of whole term. Okay. Now applying this, we have xt equals to Laplace inverse Laplace transform of all the terms plus inverse Laplace transform of this. So we are breaking it into two parts. First is this part and second is this part. This is our first part and this is second part. First we will calculate this inverse Laplace transform. Now inverse Laplace transform of Si minus A inverse, this is what our state transition matrix phi s. And inverse Laplace transform of phi s is what? Phi t. And x0 is as it is. Now we know that this phi t, it is what? E raised to the power at and x of 0. So we have obtained the inverse Laplace transform of this first part. Now second part we have Si minus A inverse B U S. So it will be 0 to t we have this is also our again the state transition matrix, and then it is multiplied with BUS. So if we write it in the Laplace transformation form, then it will be 0 to t e raised to the power a t minus x bux dx. So this is the inverse Laplace transform of first part, this is inverse Laplace transform of second part. So our complete solution will become, this is xt, then inverse Laplace transform of first part is e raised to the power at x of 0 plus inverse Laplace transform of second part is 0 to t e raised to the power a t minus x b ux dx. So this equation, xt equation, it is the solution of the non-homogeneous state equation. Non-homogeneous when we are considering our input ut. So we can say that this equation is the solution of the non-homogeneous state equation. Now, if you can see that this equation is having two parts. Okay, first part is this and second part is this. So this first part, it is representing the solution of the homogeneous state equation, and the second part, it is representing the solution of the non-homogeneous state equation. Now in homogeneous state equation, we take our input as 0. So in first part, you can see that no input term is involved. And in the second part, we have our input. So it is the solution of the non-homogeneous state equation. So we can see that this equation is having two parts. First part is e raised to the power 80 x of 0, and this represents the solution of homogeneous state equation. And second part is 0 to t. This is the solution of non-homogeneous state equation. So in this video, we have studied that how we can find out the solution of the time invariant state equations. The time invariant state equations were of two types, homogeneous and non-homogeneous, and we have studied the solution for both these type of state equations. So I hope this topic is clear to you. Thank you.